In March 1960, a Royal Air Force cargo plane soared above the dense jungles of Sarawak, far from the bustling city of Changi, Singapore. Its destination was Bario, a cluster of small villages tucked high in the Kelabit Highlands, perched nearly 3,300 feet above sea level in what was then British Borneo. While the arrival of supplies by air was nothing unusual for these remote communities, this particular drop was unlike any other. Woven baskets descended by parachute, each carrying live cats. Yes, you heard that right, cats. Well, if you're wondering, today we'll reveal why they dropped thousands of cats on an infected island. Let's start from the very beginning. Malaria Eradication Campaign. In the early 1960s, the rugged highlands of Bario, nestled within the Kelabit Highlands of Sarawak, represented one of the more isolated and culturally rich regions of British Borneo. At an elevation of approximately 3,280 feet, Bario was home to the Kelabit people, an indigenous community renowned for their traditional agricultural practices and intricate social structures. This region, composed of roughly a dozen small villages scattered across the high plateau, remained largely untouched by rapid modernization, with limited access to the outside world except through occasional air supply drops or arduous jungle treks. In March 1960, Sarawak was still under British colonial administration, part of a patchwork of territories managed by the British Empire across the region. Sarawak, alongside Sabah and Malaya, was on the cusp of transformation that would culminate in the formation of Malaysia in 1963. However, in 1960, the region was still governed by colonial officials operating out of Kuching, the capital of Sarawak. The colonial administration sought to maintain stability and promote development projects that balanced economic interests with the welfare of indigenous populations. Despite these efforts, logistical challenges posed by the dense jungles and mountainous terrain limited direct intervention, leaving many highland communities like Bario reliant on traditional methods and periodic external assistance. In March 1960, a Royal Air Force cargo plane, loaded with cats, soared over this territory. But why was it here? And what good could have possibly come from airdropping cats? Well, it all started with mosquitoes. Before the now famous cat drop in Bario, Sarawak's public health efforts were squarely focused on tackling one of the region's most pervasive and deadly threats, malaria. In the mid-20th century, malaria was not just a local nuisance, but a global scourge that affected millions, particularly in tropical and subtropical zones like Southeast Asia. This disease, transmitted by the Anopheles mosquito, was responsible for high morbidity and mortality rates. The drive to eradicate malaria was gaining unprecedented momentum worldwide, especially after the 8th World Health Assembly in 1955 declared the global eradication of malaria an achievable goal. Sarawak, under British colonial administration, was no exception. Recognizing malaria as a critical obstacle to social and economic development, colonial health authorities launched a series of aggressive malaria control campaigns in the early 1950s. The primary method of control involved residual insecticide spraying inside residential areas. Between 1952 and 1955, extensive insecticide spraying programs were implemented in Sarawak, including the remote highland communities of Bario. The two principal chemicals used were DDT, or dichlorodiphenyl trichloroethane, and benzene hexachloride, or BHC, both known for their potent insecticidal properties. DDT, in particular, had gained widespread acclaim after its successful use during the Second World War to control malaria among Allied troops and civilian populations. Its residual effect, persisting on sprayed surfaces for weeks or months, made it a valuable tool in malaria control efforts in areas where continuous spraying was logistically difficult. In Sarawak, the insecticide campaigns were conducted with remarkable thoroughness. Health workers, often accompanied by local assistants, systematically sprayed the interiors of houses, focusing on walls, ceilings, underbeds, and other typical mosquito resting spots. Spray operators used handheld compression sprayers to apply thin, even coats of DDT or BHC emulsions on interior surfaces. Quality control was critical, as inadequate coverage reduced effectiveness, while over-application increased toxicity risks. The logistics of conducting such campaigns in remote, mountainous regions were formidable. Supplies and personnel had to be transported over difficult terrain, often by small aircraft or riverboats, with weather conditions frequently complicating operations. Entomological monitoring involved capturing mosquitoes using light traps, human bait catches, and resting collections from sprayed surfaces. These data informed decisions about the frequency of spraying rounds and the effectiveness of insecticides. The campaign's initial success in reducing infected mosquitoes was attributed to rigorous monitoring and community compliance, but it also depended heavily on environmental factors such as rainfall and temperature, which influenced mosquito breeding cycles. In any case, community education efforts accompanied the spraying to encourage acceptance and cooperation. Initially, these measures yielded impressive results. Within a 21-month period, entomological surveillance recorded a dramatic drop in the proportion of malaria-infected mosquitoes from 35.6% before spraying to just 1.6%. This decline translated into fewer malaria cases, improved community health, and a sense of optimism that malaria might soon be controlled in the region. However, this success came with unforeseen ecological consequences. While DDT was lethal to mosquitoes, it was not selective in its toxicity. The chemical persisted in the environment, accumulating in the food chain and affecting non-target species. DDT is a lipophilic compound that bioaccumulates in fatty tissues and resists degradation. As a neurotoxin, DDT disrupts the normal functioning of nerve cells, leading to tremors, seizures, and death in susceptible animals. Among the affected animals were domestic cats, which played an important ecological role in controlling rodent populations. Cats, being natural hunters, would catch and consume rodents infested with DDT residues. In grooming themselves, these cats inadvertently ingested toxic amounts of DDT, which affected their nervous systems and caused widespread mortality among local cat populations. The loss of cats in Bario had a ripple effect on the ecosystem and local agriculture. Without their natural feline predators, rat populations began to surge unchecked, leading to increased crop damage and food insecurity. This unintended consequence created a secondary crisis, compounding the challenges already faced by the indigenous communities. Rats did even more damage than malaria. Resulting ecological imbalance, rat population boom. Inherently adaptable and opportunistic, rats quickly seized the ecological void left by the cats. In the dense, verdant rice fields and forest edges surrounding Bario's cluster of villages, these rodents found a near-perfect habitat rich in food and shelter. Normally cautious and kept in check by predators, the rats began to display unprecedented boldness, invading homes, granaries, and cultivated fields with growing impunity. The ecological imbalance quickly translated into an agricultural emergency. Rice, the staple crop and a vital source of food and income for the Kelabit people, suffered the brunt of the damage. Rats consumed seeds before planting could even occur, destroyed young seedlings by gnawing at their roots and shoots, and ravaged mature grains during harvest. In addition to direct crop consumption, rats burrowed extensively beneath the rice field embankments, compromising their structural integrity. These embankments, essential for water retention and proper irrigation, were weakened by the rodents' tunneling, causing water leaks, flooding, and subsequent crop failures. This destruction was both visible and insidious, undermining the agricultural cycle at multiple stages. The rapid population growth of rats was a key factor exacerbating the crisis. Rats reach sexual maturity quickly, typically between 3 and 5 months of age, and have remarkably high reproductive rates. A female rat can give birth to litters ranging from 6 to 12 pups, with a gestation period of about 3 weeks. Under optimal conditions, a single pair of rats can produce between 4 to 7 litters annually. The offspring themselves mature rapidly, contributing to a compounding effect that can yield an astounding number of descendants within a single year. Ecological models estimate that one breeding pair, left unchecked, could theoretically produce up to 1,500 rats in 12 months, though natural constraints often limit this in practice. Still, the population explosion in Bario approached this theoretical maximum due to the absence of natural predators and the abundance of food. The consequences for local food security were dire. Rice losses due to rat predation translated into lower yields, which in a subsistence farming context meant reduced food availability for the entire community. Given the isolated nature of Bario, situated at roughly 3,280 feet above sea level in the Kelabit Highlands, reachable only by arduous footpaths or infrequent airdrops, external food aid or supplemental supplies were limited. This made the agricultural disruption a direct threat to the livelihoods, health, and well-being of the indigenous Kelabit people. The ecological imbalance also heightened public health risks. Rats are notorious vectors for several zoonotic diseases, including typhus and plague, which posed additional dangers to a population already vulnerable due to limited healthcare access. Rat-borne diseases spread through fleas and direct contact with contaminated food or water, raising concerns about outbreaks that could further destabilize the fragile community. The mounting rat infestation made disease prevention a challenging task, stretching the capacity of local health services and colonial administration efforts already focused on malaria and other pressing health issues. Efforts to control the rat population initially relied on traditional methods such as trapping, hunting, and the use of poisons. However, these methods were largely ineffective at the scale required. Trapping was labor-intensive and only impacted small numbers of rats. Hunting cats was an impractical solution since the population was already depleted and the terrain was difficult to navigate. Chemical rodenticides were used, but presented risks of secondary poisoning to other wildlife and were difficult to deploy widely in remote, uneven highland terrain. The mounting crisis pushed colonial administrators and public health officials to re-examine the ecological dynamics at play. The initial success of the malaria eradication program, while significant, had overlooked the interconnectedness of species and the cascading effects of disrupting predator-prey relationships. The situation demanded an innovative response that could simultaneously restore predator presence and limit the rat population. This realization culminated in the famous cat drop operation in March 1960, scientific investigation of the rat problem. Initially, the rampant infestation of rats was approached as a typical environmental problem common to tropical highland agricultural zones. Early hypotheses favored natural factors such as climate variability, elevated humidity, and abundant food supplies as primary drivers. However, as field reports and agricultural losses mounted, it became clear that conventional explanations were insufficient to account for the scale and rapidity of the rat explosion, prompting a more detailed and multidisciplinary inquiry. Throughout the late 1950s and early 1960s, environmental scientists, entomologists, and public health experts from British colonial administrations and affiliated institutions collaborated to examine the problem. Initial field assessments in Bario documented unusually high rat densities within rice paddies and village perimeters, with local farmers reporting significant crop losses and property damage. It was widely accepted that tropical conditions could facilitate rapid rodent breeding cycles and year-round food availability, which in turn promoted rodent population growth. Nonetheless, these factors were regarded as baseline conditions typical of the region, and therefore insufficient to explain the sudden surge in rat numbers. Attention soon shifted to pest management practices, particularly the use and distribution of rodenticides. The colonial agricultural department had traditionally relied on poison bait stations and sporadic trapping efforts to manage rat populations. However, logistical challenges such as the remoteness of the Kelabit Highlands, rugged terrain, and sparse infrastructure severely limited the scale and effectiveness of these methods. Surveys revealed inconsistent applications of rodenticides, with many villages lacking adequate supplies or trained personnel to carry out systematic baiting campaigns. This deficiency was initially thought to be a major contributor to the escalating rat problem. Amid these considerations, experts began investigating the aftermath of DDT spraying. Toxicological investigation, spearheaded by teams from the Centers for Disease Control and Prevention, or CDC, in Atlanta, Georgia, brought a new level of scientific rigor, deploying advanced chemical assays and toxicological analysis to test tissue samples from deceased local cats collected during field expeditions. The analyses confirmed alarmingly high concentrations of DDT residues in the biological tissues of dead cats. These residues were far above levels considered safe, indicating chronic exposure through environmental contamination and bioaccumulation. The mechanism of toxicity was linked to cats ingesting DDT, while grooming themselves after preying on rodents and insects contaminated with the insecticide. Neurological impairment, loss of motor coordination, seizures, and eventual death were common symptoms documented in these cats, aligning with the known effects of organochlorine pesticides on mammalian nervous systems. While this finding provided a solid biochemical basis for the decline in cat populations, the question remained whether this cat population collapse directly caused the rat infestation. Some experts initially argued that the explosive increase in rats could be attributed to multifactorial causes, including seasonal climatic shifts, changes in agricultural practices, and insufficient use of rodenticides. They cautioned against oversimplifying the situation. However, the correlation between DDT use, cat mortality, and the subsequent rise in rat populations was strong and compelling. Ecological modeling and field observations supported the hypothesis that the removal of a key predator, cats, had destabilized the local food web. Without their primary natural predator, rat populations faced little biological resistance, allowing for exponential growth beyond the carrying capacity that would normally regulate their numbers. The investigation incorporated detailed population surveys, tracking rodent densities before and after the DDT spraying campaigns, and mapping the geographic distribution of cat mortality incidents. These studies showed a clear temporal and spatial association. Areas subjected to more intensive and frequent DDT application coincided with higher rates of cat deaths and more severe rat infestations. Satellite villages, less exposed to chemical spraying, retained healthier cat populations and reported comparatively fewer rat problems. Moreover, it became clear that DDT residues persisted in the environment far longer than anticipated. The insecticide's lipophilic nature caused it to bind to soil particles and bioaccumulate in the food chain, extending its toxic impact across multiple species over time. This persistence meant that even after active spraying ceased, residual contamination continued to affect non-target fauna, maintaining the pressure on predator populations and prolonging the imbalance. The scientific investigation also assessed the effectiveness of existing rodent control measures post-DDT spraying. It became evident that chemical poisons used against rats were not only limited in scope, but also less effective due to behavioral adaptations of the rats and possible bait shyness. Coupled with the loss of biological controls, the environment became a near-perfect storm favoring rat dominance. The culmination of this body of scientific work influenced the design and implementation of the novel solution adopted in March 1960. While environmental factors and pest control limitations played contributory roles, the overwhelming evidence pointed to the loss of feline predators as the pivotal factor driving the rat population explosion. The collaboration between colonial authorities, international health agencies, and scientific institutions, such as the CDC, enabled a comprehensive understanding of this complex problem. But that's not the full extent of the damage caused by DDT. Broader environmental and ecological effects of DDT. The widespread use of DDT in the mid-20th century marked a turning point in the battle against vector-borne diseases such as malaria. Yet, the chemical's environmental legacy revealed a far more complex and troubling story, especially in ecologically sensitive regions like the Kelabit Highlands of Bario and beyond. While the initial focus of DDT spraying campaigns was the dramatic reduction of Anopheles mosquitoes responsible for malaria transmission, the collateral effects on non-target species and entire ecosystems were profound and multifaceted. One of the less obvious but significant impacts of DDT spraying was the rise in moth larvae populations. In Bario and similar tropical highland regions, local ecosystems depended heavily on parasitoid wasps, particularly species from the Chalcididae family, to regulate insect herbivore populations naturally. These tiny wasps played a vital role as biological control agents, laying their eggs inside or on caterpillars and moth larvae, thus limiting outbreaks of these herbivores. However, repeated exposure to DDT decimated these populations, breaking this critical predator-prey dynamic. As a result, moth larvae flourished unchecked. The surge in caterpillar populations had direct consequences for the region's traditional lifestyles and infrastructure. Locally thatched straw roofs, constructed from natural plant fibers, suffered increased damage from voracious caterpillar feeding. Villagers who depended on these roofs for protection against the frequent rains and humid climate faced escalating maintenance burdens. The integrity of homes was compromised, increasing vulnerability to the elements and threatening the cultural continuity of traditional architectural practices. This cascading effect extended further into avian populations, creating an eerie and haunting silence in once vibrant forest and village landscapes. The application of DDT led to marked declines in local bird species, a phenomenon recorded both anecdotally by villagers and systematically through wildlife surveys conducted by colonial naturalists and ecologists in the late 1950s and early 1960s. Birds, occupying the higher trophic levels, were particularly susceptible to the bioaccumulation of DDT and its metabolites through the food chain. Consuming contaminated insects, fish, and small mammals exposed them to toxic concentrations of the insecticide, which accumulated in fatty tissues over time. One of the most devastating effects observed globally, and relevant to Sarawak's situation, was the thinning of eggshells in predatory and fish-eating birds, notably species like the American brown pelican and the bald eagle. Although these species were not native to Bario, their plight was emblematic of DDT's far-reaching ecological damage. The chemical interfered with calcium metabolism in birds, resulting in fragile eggshells that frequently cracked or failed to withstand the incubation process. This led to sharp population declines and, in many areas, local extinctions, profoundly altering ecosystem dynamics. In Bario and the wider Sarawak region, similar declines were observed in native bird species crucial for insect control and seed dispersal. With bird populations plummeting, insect herbivores beyond moth larvae, including beetles and other pests, also experienced population increases, further destabilizing the natural checks and balances. This loss of avian biodiversity not only reduced natural pest regulation, but also affected pollination and seed dispersal. This impaired forest regeneration and long-term ecological health. Unlike many pesticides that degrade quickly, DDT's chemical stability meant it persisted in soils, sediments, and water bodies for years, even decades, after application. This persistence ensured that its toxic effects echoed through time, affecting multiple generations of wildlife and compounding the damage across trophic levels. In aquatic ecosystems, for instance, DDT contamination affected fish populations, with repercussions for fish-eating birds and humans reliant on these resources for sustenance. This interconnected web of consequences highlighted the limits of human understanding and intervention at the time. The initial malaria eradication campaign had rightly prioritized human health, a pressing and legitimate concern in a region plagued by debilitating disease. However, the insufficient consideration of ecological feedback loops and secondary effects led to unintended outcomes that sometimes rivaled the original problem in severity. The loss of cats due to DDT toxicity caused the rat explosion, while the decimation of parasitoid wasps and birds contributed to outbreaks of other pests and the degradation of habitats. Scientific studies in the United States and Europe during the late 1950s and early 1960s, such as those conducted by Rachel Carson and highlighted in her seminal 1962 book Silent Spring, documented similar patterns of ecological disruption. Carson's work catalyzed the environmental movement and led to critical policy changes, including restrictions and eventual bans on DDT in many countries by the 1970s. Yet, in developing regions like Sarawak, the chemical's use persisted longer due to the pressing urgency of controlling malaria and other vector-borne diseases and the lack of safer alternatives. Colonial health administrators and environmental scientists eventually recognized the necessity of integrating ecological considerations into public health initiatives. Efforts to restore ecological balance in Bario included biological control projects. Moreover, ongoing ecological monitoring programs were established to assess the long-term impact of DDT and other pesticides on wildlife populations and habitat health. These programs employed pioneering techniques in chemical residue analysis, wildlife population censuses, and habitat mapping, providing valuable data that informed future environmental policy. Now, we come to the pinnacle of our story, the unique RAF cat drop solution. British colonial administrators, in consultation with wildlife experts and military logisticians, formulated the plan to airdrop cats into the remote Bario region. The logistical complexity of this operation was significant. Bario, situated at approximately 3,280 feet above sea level, is a cluster of about 13 to 16 small villages scattered across rugged, forested terrain inaccessible by road during much of the year due to heavy monsoon rains. The only practical means to deliver live animals and supplies was by air. Malcolm McSporran, the district officer stationed in Bario at the time, played a pivotal role in initiating the cat drop. After experiencing firsthand the severity of the rat infestation, highlighted by an incident where a rat chewed through his pillow, McSporran coordinated with the Royal Air Force to organise the airdrop of cats to combat the burgeoning rodent population. Tom Harrison, the British colonial administrator and ethnologist, also contributed to the operation. Harrison had previously attempted to arrange for cats to be flown into Bario via Borneo Airways, but logistical challenges, including the short airstrip, rendered this plan unfeasible. Subsequently, McSporran's coordination with the RAF became the primary means of delivering the cats. On March 13, 1960, the plan was executed with precision. A Royal Air Force Blackburn B-101 Beverley, a heavy transport aircraft renowned for its large cargo capacity and short takeoff and landing capabilities, took off from RAF Changi Air Base in Singapore. The Beverley was selected specifically for this mission due to its ability to carry bulky loads and operate from shorter runways, making it ideal for supporting remote operations in the region. The aircraft was loaded with approximately 3 tons of supplies intended for Bario and its inhabitants. Among the cargo were over 20 live cats, carefully packed in custom-designed ventilated crates to minimize stress and injury during the drop. Each crate was rigged with parachutes engineered to open reliably, ensuring a soft and safe landing for the animals. The meticulous planning extended beyond the mere transportation of the cats. Recognizing the cultural significance and the necessity of maintaining good relations with the indigenous Kelabit community, the cargo also included medical alcohol and a few bottles of stout beer, gifts intended for the local chieftain. This gesture reflected the British authorities' sensitivity to the social dynamics and their desire to foster cooperation and goodwill. Ensuring the local leaders' support was critical for the successful reintegration of the cats into the community, as they would oversee the care and management of the animals post-drop. The cats, upon landing, were expected to acclimate quickly to the environment, resume their natural hunting behavior, and begin controlling the rat population effectively. Early reports from the region indicated a promising start. The cats thrived, repopulated quickly, and helped to bring the rat numbers down substantially over the subsequent months. Villagers noted a visible reduction in rat sightings and damage to rice fields, lending credence to the operation's success. But wait, why didn't these new cats die of DDT poisoning? By the time of Operation Cat Drop, the intensive indoor residual spraying campaigns with DDT and BHC had significantly wound down or shifted in strategy. After the initial success of malaria control campaigns in the early to mid-1950s, there was a growing awareness of DDT's unintended side effects. In response, by 1958 and onwards, local health authorities, including the Sarawak Department of Medical Services, then led by Dr. Robert C. Stott, began modifying their approaches. The residual spraying campaigns were scaled back in certain areas, and less aggressive use of DDT was implemented, especially in places where the ecological damage was evident. When the RAF conducted the cat drop in March 1960, the levels of residual DDT in the environment, especially in homes where the cats were likely to roam, had declined, both due to natural degradation over time and because fewer new applications were being made in the Bario area. DDT, though persistent, doesn't remain in lethal concentrations forever, especially in open environments with rain and microbial activity. Additionally, the new cats were less exposed to the immediate sources of DDT contamination than the earlier generation. The earlier cat deaths had occurred primarily through grooming after hunting rats or insects that had ingested DDT, or through contact with freshly sprayed surfaces in homes. With the spraying campaigns less aggressive by 1960 and the residue levels lower, the risk of acute DDT poisoning had reduced. Moreover, the cats were dropped into Bario after the peak of indoor spraying operations, allowing them to perform their role as natural rat predators without the same level of environmental risk. But wait, there's more to our story. From a technical standpoint, the RAF's choice of the Blackburn Beverley was pivotal. Introduced into service in 1956, the Beverley was specifically designed for heavy cargo transport and airborne operations. With a payload capacity exceeding 35,000 pounds and a spacious cargo bay measuring 63 feet long, 11 feet wide, and 12 feet high, it could accommodate both animals and essential supplies simultaneously. The aircraft's robust parachute deployment systems and experienced RAF aircrew ensured that the cat crates were delivered intact. The deployment method drew on principles from airborne military supply drops and paratrooper insertions, tailored to meet the sensitive needs of live animal transport. The cat drop was also remarkable for the pioneering use of what would later be recognized as an early form of biological pest control delivered via aerial means. At a time when ecological considerations were not yet mainstream in pest management, the operation demonstrated an intuitive grasp of ecosystem interdependencies. Instead of relying solely on toxic chemicals, which had already proven harmful, the British authorities harnessed natural predators to restore ecological balance. The immediate and instinctive response of these airdropped cats was to hunt the explosive rat population that had been running rampant due to the collapse of natural predator populations caused by earlier DDT spraying. This swift action by the cats was instrumental in beginning the restoration of ecological balance in the region, where rice paddies and subsistence crops were under siege from voracious rodent swarms. As the cats took to their new roles as natural rodent hunters, the results quickly became evident. Villagers in Bario reported noticeable declines in rat activity, reduced crop damage, and improvements in overall food security. This biological control method proved more sustainable and ecologically sound compared to the earlier chemical interventions that had led to unintended environmental damage. The cat's hunting curtailed the rat population growth, reducing the pressure on rice fields and other vital agricultural areas. Over the following months, the balance between predator and prey began to stabilize, demonstrating the effectiveness of this approach to curb pest outbreaks. Moreover, the lessons learned from the Bario incident, along with other similar ecological disasters worldwide, contributed to growing scientific scrutiny of persistent organic pollutants, particularly those like DDT that bioaccumulate in the food chain. As awareness grew, research into safer, biodegradable and species-specific alternatives to broad-spectrum chemicals like DDT accelerated. By the late 1960s and 70s, scientists began developing integrated pest management strategies, emphasizing a combination of methods like crop rotation, biological control, habitat management, and limited, targeted use of pesticides. At the same time, chemical companies and agricultural scientists explored non-toxic or less toxic alternatives to DDT, such as pyrethroids and organophosphates, which, while not perfect, degraded more quickly in the environment compared to DDT. The Bario episode also influenced the gradual international policy shift against DDT. By the 1970s, many countries, including the United States, Norway, Sweden, and Canada, had either banned or severely restricted DDT use. These bans culminated in the Stockholm Convention on Persistent Organic Pollutants, decades later, in 2001, which globally restricted DDT usage, limiting it only to specific disease control cases like malaria in exceptional circumstances. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.